How's it going? Today we're looking at 1.3 complex numbers. This is like imaginary numbers. It seems like a weird thing to get thrown in here when we've been solving equations, but it's sort of a prep lesson to get us ready for what's coming. Before we just jump in here and doing computation on complex numbers, let's distinguish an imaginary number from a complex number. Now, an imaginary number is one that you should be familiar with. It might be something like, I don't know, maybe 5. Oops, let me get my pen here. It might be something like 5i. That would be an imaginary number. You would get that by taking the square root of a negative 25. And we would break that down into the square root of a negative 1 and the square root of a 25. The square root of 25 is just a 5, and this right here, the square root of negative 1, is what we define as an imaginary value I. And so those get multiplied, and that's where we get our 5i from. A complex number is a little bit more comprehensive. A complex number will often have a real part attached to an imaginary part. So the format is usually something like a plus bi. So something like that might be like 7 plus 5i, where it has a real part and it has an imaginary part to it. So a complex number, it usually in this format. Now, that doesn't mean that this can't also be considered complex. It just means that the real part would have been a 0. Complex number kind of incorporates everything, because think about if b was 0. If b was 0, then it would just be a real number right here. So let's jump in and work through these like you have done before. You must always address the imaginary number first. In other words, you can't ignore the fact that you're trying to take the square root of a negative. So this one right here would be just like what I had done earlier. You would split this up. It'd be the square root of a negative 1 and the square root of 16. All right, so there's my I, there's my 4. So we would write this as 4i. Now, the order that I do these two things in does not matter. So futuristically, I might want to swap those so that my I is just naturally on the back end and I don't have to rewrite it here. Okay, let's try this one. Not quite as straightforward because 70 is not a perfect square. So what's the perfect square that goes into 70? Well, there actually isn't one. So the way that this would look, you'd have your square root of 70 and you'd have your square root of negative 1. And so it could be written the square root of 70i. Now, sometimes you'll also see that written I square root of 70. In all honesty, I prefer this method because we don't accidentally get this I tucked underneath the radical, because it should not be. It has to be separate. So this is the preferred method, by me at least. I'm not saying that you won't find it written this way other places. All right, one more, square root of 48. This one does break down. So I'm going to break it down with everything that comes out nice. You could have your square root of 16 goes into it 3 times. I'm going to actually do this right here. See if you can figure out why I chose to break it down like this. So 16 times negative 1 times 3 gives me my negative 48. So right here is my 4i square root of 3. Now, order doesn't really matter, but this is going to be the preferred method for your final answer. All right, let's try some simplifying using some of those patterns or some of those properties we talked about. So looking at this first one, it might be very tempting to call that the square root of 49 because you just multiply the radicals together. The problem with doing the square root of 49 is you get a 7, and you never ever acknowledge that these were imaginary. You've got to start with the fact that they're imaginary. Instead of just multiplying them, you want to think of this as an I square root of 7. This one is an I square root of 7. That's going to end up getting me an I squared times 7. And I squared is negative 1. That actually gets us a negative 7 when you acknowledge that they were imaginary versus the 7 that if you didn't acknowledge it. Let's try this next one. I'm going to call this I square root of 6 times your square root of 10. Now I'm going to go ahead and multiply the radical parts together and break those down. 60 can be broken down to the square root of 4 times the square root of 15. And that's going to end up getting me a 2i square root of 15. Now again, I feel like you're going to definitely see this I tucked on the back end sometimes, but I kind of prefer it just go in the front so it's together with all the stuff that's not under the radical. Now this next one, if you acknowledge that these are both imaginary, you'd end up with an I square root of 20, I square root of 2. The root 20 and the root 2 will divide out. That works out real nice. But actually, the i's will also divide out. That's legit. You can do that. Divide the i's out. Root 20 divided by a root 2 gets us a root 10. All right, next one like this. The numerator is going to be imaginary. I'm going to have an I, and I'm going to break down that 48 into a root 16, root 3. You know what? Maybe I'm not going to do that. Do you know why? Because the 48 and the 24 will actually reduce. I might try this instead. Let's see what would happen. Not to say what I was doing wasn't going to work. I just think this is going to be faster because 24 will go into 48 twice. You're left with I square root of 2. And there's no reducing to be done then. Now, moving forward, we're going to start having more of these complex terms, complex numbers that have a real part and an imaginary part. And to write them, we call this standard form. It's a plus bi, and you separate the real part from the imaginary part. When you get a fraction like this, where it's all tied together in one term, we like to separate that out. Both the real part and the imaginary part are being divided by 4. Let's go ahead and separate them to show that. Negative 8 over 4 plus, and then this is going to be a little bit messier, but I'm going to go ahead and try to reduce. I know I'm going to have an I. And let's see, that's going to be a 64 goes in there twice. Let's clean it up a little bit. I'm going to get you a negative 2 plus 8i root 2 over 4. And the 8 and 4 conveniently reduce. Last step, negative 2 plus 2i root 2. Final answer. All right, so one thing I do want to note, that one just came out beautifully, but what if this was a 7 instead of an 8? Well, that just means this would not have reduced, and this would have stayed a fraction. But this one maybe still came out nice. That's okay. By separating it and putting it into a plus bi form, oftentimes you'll end up with one of the terms being a fraction where the other one maybe comes out without a fraction. That's okay. We want to keep them separate. All right, let's try some operations. Let's work with some operations on I. Again, remembering right here, I squared always equal to negative 1. If I'm going to come across an I squared, I'm going to convert it to a negative 1. I kind of look at i's almost like they're just x's. You're doing operations the same way. Right here, I am adding these two complex numbers. Just add like terms. You've got a 5 and a 7. That's going to get you a 12. Those are like terms. And then combine the imaginary parts. You got a negative 11i and a 4i. That's a minus 7i. Done. If you're subtracting, remember, you got to distribute that through every term here and then combine the like terms. I've got my negative 5 and my 11. I've got an I and a 6i. If you see some sort of scenario that looks like you would distribute, you just distribute. You're going to end up with a 12i minus 20i squared. And right there, remember, I squared is negative 1. So if that's a negative 1, that's actually going to turn into a positive 20. And we usually like to have the real part come first. So I'm going to call that a positive 20 and then a plus 12i, like that. Next one, let's try doing FOIL. So first, outer, inner is a plus 6i, and last is going to be a positive 15i squared. And like always, the middle two terms are going to combine. But this right here on the end oftentimes is going to have that I squared. So my plus 15 is going to turn into a minus 15 that I can combine with a negative 14. That will get me a negative 29. And then the imaginary parts are going to be a negative 29i. All right, one more, FOIL. Let's look at this. Now take a look at this one. It is different than the previous. Look at how similar these are. What do we call these? Do you remember? Those are conjugates. They're the exact same except one's a plus and one's a minus. If you multiply the first, you're going to get a 16. Outer is 8i. Inner is negative 8i. Remember that? That's the whole deal with conjugates. That will happen every time. So much so that if you know you're multiplying conjugates, you don't even have to write the outer and the inner. I would love it if you acknowledge, oh, those are going to cross off, and you're just going to write 16, and then we're going to have a minus, oh, not 2, but 4i squared. But I squared is going to change that to a plus 4. Final answer is going to be 20. All right, the last one, you're taking a binomial and squaring it. Remember that squaring powers don't distribute. This distribution is with multiplication, not with powers. So don't do that. I had people doing that on their tests still. Don't do that, please. Instead, what I'd really like you to be doing is using the shortcut that we've talked about. Now, if you have to write it out and do FOIL on it, you do that, but it's just an efficiency that we should be working towards, that to square a binomial, you square the first term, you multiply the 2 and double it. That's going to get us a plus 12i. And then you square the last term. That's going to be a 9i squared. You're going to change that to a minus 9 that you can combine with your 4. Negative 5 plus 12i. Always put the real part first. Now, the whole idea of dealing with those conjugates or talking about those conjugates is because we use that strategy to try to rationalize our denominator. Now, rationalize usually means like to get rid of the radical, but I is really a square root of negative 1. So even having an I in the denominator is not preferred. We will take the time to go ahead and rationalize this the same way we did as if it was a radical. We'll go ahead and multiply by the conjugate, and you'll do it on the top and the bottom. In your numerator, let's go ahead and FOIL. Denominator, they're conjugates. Outer and inner are going to cancel. I'm going to get a 4, and then it's going to be a minus 25i squared. Clean up our numerator. This is really negative 20 that I can group with the 16. That's going to be a negative 6. The 35 and 8 will combine to 43i. This becomes a plus 25. So then I have a 29 here. And then this is like I had on that previous slide where we want to separate the real part from the imaginary. So we're going to rewrite this as negative 6 over 29 plus 43/29 I. And we attach the I off the back end because this is really the coefficient on the I, the full fraction. This is called standard form. If they ask you to write it in standard form, this is what they're looking for. The real part plus the imaginary and the I is off to the right if it ends up being a fraction. Now the next term here is similar to what we would do if you just had a single radical and not a sum or a difference like we did on this one. Just like we do with radicals, you can just take it times itself. I'm going to take it times I. Then I'm going to end up with 3I over I squared, which is really, I mean, I can write I squared. I could also write -1. But a 3I divided by a -1 will get me a -3I. All right, last thing, and I think this is kind of a cool concept, but I'm kind of nerdy that way. I know that I is really, I mean, it's the square root of -1, but I'm going to write it just as an I right here. It's just an I. Now, if I have an I squared, we've already talked about, we know that's -1. I cubed, here's what I want you to think of it. I want you to think of it like it's an I squared times an I. That would be I cubed. But since I squared is -1 times I, if you were to do I cubed, you really get a -I. Let's try I to the 4th. Think of it like this. It's an I squared times an I squared. That'd be an I to the 4th. That would also be a -1 times a -1, which is a positive 1. Let's try I to the 5th. Wouldn't an I to the 5th really be an I to the 4th times an I? Now, there's different ways to write these. I'm cherry picking these so that they come out to do exactly what I want them to do. I to the 4th, we've already acknowledged is a 1. So you're just going to end up with a 1I, or just I. Let's try it with I to the 6th. Couldn't that be an I to the 4th times an I squared? Well, I to the 4th, we've already acknowledged is a 1. I squared is a -1. And 1 times -1 is -1. Now, I could keep on going, but really what I want you to notice is that this pattern right here, it goes I, -1, -I, 1. And it will start all over because it's always just an I to the 4th times the next one. And so since I to the 4th is always a 1, you start over with this pattern of I squared, I to the 3rd, I to the 4th, and it will just continue to repeat. You're going to need to remember this pattern of I, -1, I, 1. Because what we can do with that, knowing now that it's just going to continue to repeat that pattern, I could ask you much higher powers, and all you have to recognize is where would that fall in this range? Well, all multiples of 4 land right here. Multiples of 4 always will end up equaling 1. So when I look at this list, oh, looky, 28 is a multiple of 4. So I know I to the 28th is going to equal 1. But the others are not multiples of 4. So you have to look at them in reference to a multiple of 4 that it's close to. For instance, I to the 9th, well, that would just be 1 past I to the 8th. And I to the 8th is the multiple of 4. And so if it's 1 past it, it's going to start over, and it's going to be up here at an I then. So I to the 9th would be the same as an I. Let's try I to the 15th. Okay, that's close to an I to the 16th, because 16th would be a multiple of 4, but it happens right before the I to the 16th. So if this is going to be the I to the 16th, this is going to be I to the 15th. So I to the 15th is going to have to be the same as -I. Why don't you try the 42? Figure out where that would fall. All right, there's a couple ways to do that one. You could reference it close to 40, because 40 would be here. So 41, 42. So it's going to have to equal -1. But maybe instead you thought of it, oh, it's close to 44. Here'd be 44, 43, 42. still lands at a -1. So either way, doesn't matter as long as you get it wrapped around to the right spot on that string of 4 values. All right. This one should be a pretty quick assignment compared to our last one. Good luck.